So this is the 43rd video on rigid body kinematics. Okay. So this is in continuation of the 42nd video. In this also I'll take up some one or two questions on IC location, IC, and then I'll take some miscellaneous problems. Okay. So before going ahead, again I'm repeating it. If you understand the contents of this video channel, you don't have to go anywhere else. It's more exhaustive. If you go through them, you understand them properly, and then you have, I'm sure you'll be able to solve most of the problems from any source. Okay. And all the videos I will put in the playlist. You can go and access them. Okay. So I write down the question first. See, before writing the question, one thing I would like to say that one thing which I would like to say is this, that suppose M is a rigid body which undergoes plane motion with respect to F. Okay. M is a rigid body which undergoes plane motion with respect to F. Then M definitely possesses an IC. Now velocity of IC by definition is 0. Velocity of IC of M with respect to F at time t is by definition 0. But acceleration of IC need not be 0. This you must be clear about it. Why? And the reason is that at different instants, different locations of M become the IC. That is, I'll just explain it. See, this is frame F, okay? This is M is some rigid body. M is some rigid body which undergoes plane motion, plane rotation with respect to F. So let this P be the IC of F, M with respect to F at time t. Let this be the IC of M with respect to F at time t. IC, P bracket t. Let P bracket t be the IC of M with respect to F at time t. Okay. Now t plus dt at t plus dt seconds, suppose P dash becomes the IC. This means at t plus dt, P is not the IC. This means at t plus dt, velocity of P is non-zero. So at time t when P was the IC, Vp was 0. And t plus dt, Vp is non-zero. So in time t to t plus dt, velocity of point P has definitely changed. So this means that P has a non-zero acceleration at time t. So IC has 0 velocity at time t, but its acceleration at time t is in general non-zero. Because at dt seconds later, some other point of the body becomes the IC. So at t plus dt, look, P is not the IC at t plus dt. That is, at t plus dt, velocity of P is non-zero. But at time t, velocity of P is 0. So in t to t plus dt, velocity of P changes from 0 to some non-zero value. So its velocity changes. So it accelerates. So acceleration of IC at time t is in general not 0, but velocity is 0. Okay. Now I will take up a question related to this concept. Acceleration calculation of IC. So I'll write down the question. A circular wheel of radius r and center at C1 rolls without slip over a fixed vertical circular track with center at C2 and radius 4r. With center at C2 and radius 4r. The center C1 of the wheel moves at a constant speed v with respect to ground. At the instant shown, find the acceleration of IC of wheel with respect to ground. Okay, find the acceleration of IC of wheel with respect to ground. So I draw the diagram of the situation. So this is the circular track. This is the center C2. This radius is given to be 4r. The wheel is given to be at the highest location on the track. C1 is the center of the wheel. R is the radius of the wheel. Center C1 moves at a constant speed v. The wheel undergoes pure rolling over this track. Rolls without slip. So we have to find the acceleration of IC of wheel with respect to ground. Acceleration of IC of wheel with respect to ground at the given instant. Okay. This is a bit, okay. So now first of all, the track is fixed in vertical plane. Track is fixed in vertical plane. The wheel is undergoing pure rolling over the track. So here it undergoes pure rolling. Here the wheel undergoes pure rolling. Okay, fine. And first of all, the track is fixed. From pure rolling condition, let P be the material point of the wheel in contact with the track. P is the material point of the wheel in contact with the track. P is the material point of the wheel in contact with the track. Since the track is fixed in ground frame and point P of wheel is in contact with the track, since it is undergoing pure rolling, by criteria of pure rolling, Vp is 0. Velocity of material point P of track with respect to ground is 0. So by definition, P is the IC of wheel with respect to ground at time t. P is the IC of wheel with respect to ground at time t. Alright. P is the IC of wheel with respect to ground at time t. P is the IC of wheel with respect to ground at time t. Now we have to find the acceleration of point P. Now P is the material point of the wheel. Now in order to find the acceleration of point P with respect to ground, we have to apply SRC procedure for acceleration to the wheel between the points C1 and P in ground frame. Okay. Now for that, what we'll do, we have to first know the acceleration of point C1 of the wheel, also its angular velocity omega of the wheel, and also its angular acceleration. Now first of all, the wheel undergoes pure rolling over this and center C moves like that. So for pure rolling criteria, angular speed omega of wheel should be omega clockwise. And let beta be the angular acceleration of wheel with respect to ground. Okay, fine. Now, you can see that center C1 of the wheel is at a distance of r from ICP. So from IC concept, velocity of C1 is just omega r, that is v. So omega becomes v by r. This is the angular speed of the wheel with respect to ground, which is seen to be a constant quantity. So beta becomes angular acceleration of wheel with respect to ground, that is just d omega by dt, that is 0. Because omega is constant, v is constant, r is radius fixed. So v by r is constant, so derivative of omega with respect to ground is 0. So beta angular acceleration of wheel with respect to ground is 0. So omega becomes constant and beta becomes 0. Alright, fine. Now what I do, I apply SRC procedure for acceleration between the points C1 and P. Actually, one more thing, before applying SRC procedure, we must also know the acceleration of center C1 of wheel with respect to ground. Now you can see center C1 of wheel with respect to ground moves in a circular path whose center is at C2 and whose radius is r plus 4r 5r, and C1 moves at a constant speed v. So from theory of circular motion kinematics of point, acceleration of c1 will have two components. A component along tangent, that is in this direction, and component along inward normal, that is along this direction. Suppose unit vector in this direction is e1 hat and unit vector in downward direction is e2 hat. So AC1 will be what? AC1 will be AT E1 hat plus AN E2 hat. Now AT is the tangential acceleration of center C1, but center C1 moves at a constant speed v. So tangential acceleration of center C1 is dv by dt, which is 0 because speed is constant. So this term goes away. We are left with AN. AN is the normal acceleration of center C1. Now C1 moves in a circle with center at C2 and radius 5r at a constant speed v. So normal acceleration becomes v square by 5r into E2 hat. So this is AC1. The acceleration of center C1 of wheel with respect to ground is v square by 5r E2 hat, and that is in downward direction. Now I apply SRC procedure for acceleration to the wheel between the points C1 and P in ground frame. So SP, selected point becomes what? Selected point becomes C1, and other point becomes what? Other point becomes P, that is IC. Now I draw the line joining C1 and IC, that is C1 and P. I give the acceleration of C to point P. Acceleration of C is v square by 5r in downward direction. So I give this acceleration v square by 5r to P in downward direction. Alright, I give the acceleration v square by 5r to P in downward direction. Now I write down the sentence. Omega is clockwise. So P moves in a clockwise circle with center at C1 and radius r. So P should be given two accelerations. Omega square r to point P towards C and r beta along leftward direction. But beta is 0, we know. So this term drops out. So acceleration of P is the vector sum of these two terms. This term drops out. Now omega square r. Omega is how much? V by r. So this becomes v square by r square into r. V square by r. So this term is more than v square by 5r. So acceleration of P with respect to ground, that is acceleration of IC with respect to ground, is simply the vector sum of these two. So this is just equal to omega square r minus v square by 5r. Alright, fine. So omega square r is v square by r. This becomes how much? This becomes v square by r minus v square by 5r. So acceleration of P with respect to ground becomes v square by r minus v square by 5r, that is 4v square by 5r in upward direction. That is therefore the required answer. So acceleration of IC of the wheel with respect to ground at the given instant is 4v square by 5r in vertically upward direction. So acceleration of IC of wheel with respect to ground at time t has a magnitude of 4v square by 5r and is directed in vertically upward direction. It is therefore the required answer to this problem. I hope you understand this point. Okay. So in this problem I have demonstrated that acceleration of IC is in general non-zero. Acceleration of IC is in general what? Non-zero. This I have demonstrated. Fine. Alright. So this I will rub it now. Okay. This I rub it, okay. Now, this was the last problem on IC, okay. So question IC is finished. Now what I do, I take some additional miscellaneous problems on rigid body kinematics, okay. And then this chapter will be finished. We'll then start with take the chapter on Newton's laws of motion phase 1. So that I think 100 videos will be made, okay. I will tell you more than 100 also, it will be less also. But definitely 70 to 80 video definitely there will be, there is no doubt. So now I take up the next question, okay. So this question is on irodove. Okay, this question is from irodove. Okay. So the problem is this: a rigid body B1 rotates at a constant angular velocity omega 1 equal to omega 1 I hat with respect to ground. A rigid body B1 rotates at a constant angular velocity omega 1 with respect to ground. And another rigid body B2 rotates at a constant angular velocity omega 2 equal to omega 2 j hat with respect to ground. Okay, where omega 1 and omega 2 are positive constants. I hat and j hat are respective unit vectors along x and y axis respectively. Now two things we have to determine. Find first relative angular speed of B2 with respect to B1. Angular speed of B2 with respect to B1. And second, magnitude of angular acceleration of B2 with respect to B1. Magnitude of angular acceleration of B2 with respect to B1. These two things we have to determine, okay? So the solution to this problem is in this way. We apply the general formula. See here, three rigid bodies are under consideration. First is body B2, then the body B1, and then finally ground frame G. Finally G is the ground frame, okay? So these are the three rigid bodies under consideration. Now, first part of the answer question I solved now. So now it was shown in the, you'll get in the beginning chapter of rigid body kinematics. You open that playlist, you go there. In the first video on rigid body kinematics, or second video, first, second, third video, you'll get all the details, okay, this theory. You just refer to that video, that will be sufficient. So, angular velocity of 2 with respect to g, omega 2g, is equal to angular velocity of 2 with respect to 1, omega 21, plus angular velocity of b1 with respect to ground, that is omega 1g. Okay, so we have to determine the magnitude of omega 21. So omega 21 is the angular velocity of body b2 with respect to body b1. That is just omega 2g minus omega 1g. Now omega 2g is how much? Omega 2g is omega 2j hat. And this is omega 1 I hat. Now we have to determine, this is the relative angular velocity of b2 with respect to b1. But we have to determine the relative angular speed of b2 with respect to b1. The relative angular speed of b2 with respect to b1 is just the magnitude of this vector, which is root under omega 2 square plus omega 1 square. This is the answer to the first part of the question. So relative angular speed of b2 with respect to b1 is root under omega 2 square plus omega 1 square. This is the answer to the first part of the question. Alright. Now I love this one, okay? Now solve the second part of the question. Second part is this. Angular acceleration of body 2 with respect to ground beta 2g is equal to angular acceleration of body b2 with respect to body b1 plus angular acceleration of body b1 with respect to ground frame minus omega 21 cross omega 1g. So this expression also you get in the first or second video on rigid body kinematics, okay? You search those things, you'll get it there. You just go through the playlist, you'll get it. So this becomes beta 2g becomes beta 21 plus beta 1g plus omega 21 cross omega 1g minus omega 21 cross omega 1g. So from this we see that beta 21 is beta 2g minus beta 1g. This term goes right side, left side. I mean other side. Omega 21 cross omega 1g. Now beta 2g is d by dt of omega 2g in ground frame. Beta 1g is d omega 1g by dt in ground frame plus omega 21 cross omega 1g. Now this term drops out because omega 2 angular velocity of body 2 with respect to ground is constant. So derivative of constant is 0. This term goes away. Omega 1g is angular velocity of body 1 with respect to ground, that is constant. So derivative of constant is 0. These two terms goes away. Now omega 21 we know how much. Omega 21 is omega 2g minus omega 1g. This I substitute here. Omega 2g minus omega 1g cross omega 1g. So this becomes omega 2g cross omega 1g minus omega 1g cross omega 1g. This term drops out from property of cross product. So beta 21 angular acceleration of body 2 with respect to body 1 is omega 2g cross omega 1g. Now omega 2g is simply omega 2j hat. Omega 1g is omega 1 I hat. So this becomes omega 1 omega 2 k hat. Okay. So this becomes beta 21. Now I take the magnitude on both sides. If I take the magnitude on both sides, then beta 21 is the equal to just omega 1 omega 2 because k hat is a unit vector, magnitude is 1. So magnitude of angular acceleration of body B2 with respect to body B1 is equal to omega 1 omega 2, and that is therefore the required answer to part 2 of the given question. I hope it is clear. Fine. Alright. So this was the second question. This was a miscellaneous problem. Okay. Fine. Now I got this one. Now what I'll do, I'll take one more miscellaneous question on rigid body kinematics. This question is also from irodove. Okay. It's the chapter on the rigid body kinematics chapter of irodove. This question you will get it there. But still I'll write down the question here. Okay. For convenience. So I'll take up one more question. I'll take up one more question on this chapter, rigid body kinematics chapter. The problem from irodove. Okay, I'll just write down the question here. Just for the sake of convenience, I'll write down the question. So, question is this. Question is this, I'll write down the question. A circular disc with circular disc rotates. Circular disc rotates with a constant angular velocity omega naught about a horizontal axis AB. Horizontal axis AB with a constant angular velocity omega naught about a horizontal axis AB. At the moment t equal to 0, the axis AB starts rotating axis AB starts what? Rotating, about turning, starts turning about the vertical axis. about the vertical axis with a constant angular acceleration beta naught. With a constant angular acceleration beta naught. Find the angular speed and magnitude of angular acceleration of the disk with respect to ground at time t in terms of the given quantities. In terms of the given quantities. In terms of the given what? Quantities. Okay, omega naught, beta naught and t. So this is the solution. First what I do, I draw the diagram of the situation. See, this is the horizontal axis AB. This is the disk. Center C of disk coincides with point B. This AB is horizontal, it has been drawn in 3D view. This is the vertical line. The disk turns at a constant angular speed omega naught about line AB. It can rotate this also, it can rotate this also. I take up suppose this one, omega naught. And this line AB turns about vertical at constant angular acceleration beta naught. So at time t we have to determine the angular speed and magnitude of angular acceleration of disk with respect to ground. This we have to determine. So first part of the answer I take up. Suppose this is a situation at time t. At time t, the angular speed of disk remains omega naught constant as it is specified in the problem. It remains omega naught constant as it has been specified in the given problem. Alright. At time t, this line AB turns at a constant angular acceleration beta naught starting from rest. So at time t, angular speed of line AC becomes, AB, that becomes beta naught t. So let omega be the angular speed of line AB at time t. That is just 0 plus beta naught t. Since beta naught is constant, so angular speed of line AB at time t is simply beta naught t. So angular speed of line AB at time t is simply beta naught t. Its direction is in upward direction. The line AB turns like this. Direction is upward. Right hand thumb rule. And this is the line AB at some instant. It is turning like this. Disk is like this. It is turning like this. Omega naught is outward direction. Right hand thumb rule. Okay. This side up now. Okay. So now see, here there are again three rigid bodies under consideration. One is a disk, which is denoted by D say. Other is this rod, denoted by R say. And last is ground, denoted by G say. Okay. Now we have to find the angular speed of disk with respect to ground at time t. Okay, fine. So we apply that formula for relative angular velocity omega dg. Angular velocity of disk with respect to ground with respect to g is angular velocity of disk with respect to rod that is line AB. Rod AB that is rod AB. It's just a rod, it's an imaginary rod. It's not a real rod, it's just imaginary rod. So instead of AB we have R. We call it R. Plus angular velocity of R that is line AB with respect to ground. Now omega dr is what? Angular velocity of disk with respect to rod. Now see, angular velocity of disk with respect to rod is like this, omega naught, outward direction. So what I do here, I define three unit vectors here. First is a unit vector along this line. Let's call it say n1 hat. First is unit vector along vertical direction. That is n2 hat. Okay. And third is unit vector, that is say, suppose this is a disk. Okay. This is n1 hat. This is n2 hat. Okay. Fine. So omega dr, angular velocity of disk with respect to line AB, that is simply omega naught into n1 hat. So this becomes omega naught into n1 hat plus angular velocity of rod AB with respect to ground, that is beta naught t in upward direction, that is along n2. So this becomes beta naught t into n2 hat. Okay. So omega dj becomes this much. Omega dj becomes omega naught n1 hat plus beta naught t n2 hat. Okay, fine. Now we have to find the magnitude of this. Angular speed is the magnitude of angular velocity. It is just this magnitude of this. Beta naught t n2 hat. Okay. Now see, beta naught t is upward direction and n1 omega naught is along this. So these two vectors are mutually perpendicular. So from the property of vector and Pythagoras theorem, it follows that the angular speed of disk with respect to ground is simply omega naught square plus beta naught t whole square. This is therefore the required answer. So an angular speed of disk with respect to ground is root under omega naught square plus beta naught t whole square. This is the answer to first part of the question. Now in second part we have to determine the magnitude of angular acceleration of disk with respect to ground in terms of the given quantities omega naught, beta naught and t. Now beta dg is the angular velocity of disk with angular acceleration of disk with respect to ground. Again, for that relative formula for beta, what do we write? Beta dr plus beta rg minus omega dr cross omega rg. Beta dr. Beta dr is the angular velocity of disk with respect to line AB. That is same as d by dt of beta dr we have to find. Beta dr is, you can tell what is beta dr. Angular velocity of disk with respect to rod. Okay. Angular velocity of disk with respect to rod. Now with respect to rod, angular velocity of disk is omega naught along constant direction. So this quantity becomes 0. This quantity drops out. Plus beta rg, angular acceleration of rod r with respect to ground. That is beta naught in upward direction, that is along n2. So this becomes beta naught n2 hat minus omega dr. Omega dr is what? Omega dr is this, omega naught n hat. Omega dr is this quantity. Cross omega rg. Omega rg is what? Omega rg is simply, omega rg is what simply? Omega rg is simply beta naught into n2 hat. And this is omega naught into n1 hat. Okay, fine. So this becomes beta naught n2 hat minus, if you interchange these two, it becomes here t also comes, t will also come here. This one, beta naught t was missed out, t was missed out. Beta naught n2 hat minus, if you interchange, omega naught beta naught t n2 hat cross n1 hat. Okay. Now rub this one. So magnitude of beta dj is this much. Now you see n2 cross n2 hat cross n1 hat is normal to n2. So these two vectors are mutually perpendicular. So magnitude of this vector beta dg is simply root under beta naught square plus omega naught beta naught t whole square. So beta naught comes outside 1 plus omega naught t whole square. This is therefore the required answer. Okay. So beta dg becomes beta naught root under 1 plus omega naught t whole square. That is therefore the required answer to the given problem. Okay. Alright. This also I have discussed now. So till here, chapter on rigid body kinematics is hereby finished. Okay. I have taken so many problems. You can see 43 videos have been made on rigid body kinematics. If you go through them all of them properly and you understand it, you don't have to go anywhere else. And you take a problem from any source on this chapter, I'm sure you'll be able to solve it. In case you have any difficulty, write down your doubt in the comment box. I'll look into it and clarify it. Okay. So I close it here. Fine. All right.